Hello. So we are continuing chapter 17, which is aqueous equilibria, and it is divided into three parts. The first part was buffers, second part is titrations, and then the third part is KSB. So today we're going to start part 2, which is titrations. And titrations are actually linked to buffers. So let's talk about what a titration is and how it links to buffers. So titration is a lab method, a lab technique, where you react two things together. Usually you have an analyte and a titrant. So the analyte is what you are studying, what you're analyzing, therefore it's called the analyte. The titrant is usually a known substance of known concentration that you add slowly to your analyte until you reach some kind of equivalence point or endpoint. So a lot of times we use titrations with acids and bases because we can use an indicator to tell us when we've reached that equivalence point. And so usually we have the base in a burette, so B, base in burette, not always, but usually. And then the acid goes into an Erlenmeyer flask with some kind of indicator. And usually you add the base very, very slowly, drop by drop, until you see a color change, depending on the indicator. And then that's when you've reached your endpoint, and usually you stop your reaction then. So the endpoint is when the indicator changes colors. Now there's tons of different types of indicators that change at different pHs. So you want to pick an indicator that will change at the pH where you reach your equivalence point. So the equivalence point is when enough titrant has reacted with the analyte. So when they're equimolar, basically, based on your stoichiometric ratios. So when you don't have any leftover reactant, right? So when they've been both used up equally. Now, for the purposes of this year, when we're doing acid-base reactions, most of our titration, or all of our titration calculations, are going to be a 1-to-1 ratio of acid to base. And so your moles of acid are going to equal to your moles of base at the equivalence point because they're a 1-to-1 ratio. So you want to stop your titration when you've reached your equivalence point, when you've added enough acid and base to react together completely. So you want to pick an indicator that has an endpoint close to where your equivalence point is. So the endpoint is when the indicator changes color. The equivalence point is when your reaction is done. So you want your endpoint where the change in color to match where your equivalence point is. So they're different things. So if you look at these titration curves, and we're going to talk about each of them in more detail, but you'll see that if you were to measure the pH in your Erlenmeyer flask where your acid is, at the beginning you start with just the acid, so you have a low pH, and you are slowly adding the base. The pH very, very, very slowly starts going up, then it shoots up suddenly, and then it starts leveling off again. So you have kind of like an S curve to your titration. And so when you are doing a titration, you'll notice that, like we said, it's moving very, very slowly. The pH is moving very, very slowly here. And the reason for that is actually you are creating a buffer when you are titrating. So if you look at the previous page, the reason or a crucial part, a big reason why a college board puts buffers into the curriculum is because buffers are a big deal in titrations, because when you are titrating a weak acid or a weak base, you actually form a buffer. So for example, let's say you have a strong acid, so like NaOH, for example, reacting with a weak acid. So a strong base reacting with a weak acid, acetic acid here. So once you add a little bit of the hydroxide, when these two react, you get water and then the acetate ion. Well, if you only added a little bit of the hydroxide so that you have leftover acetic acid, well, then you're going to have leftover acetic acid and you're going to have some acetate forming. And so acetic acid and acetate, that is a buffer. And that is why you have this portion of your S curve where it's going very, very slowly, because that's a buffering zone, meaning that we have a buffer, and so as I add my OH minus, my pH is kind of remaining steady. Once it shoots up, that's when you've used up your buffer. That's when one of the components is done. So basically, when you've added OH minus enough to use up all of your acetic acid, so that you don't have any more of the buffer, that's when it shoots up. Same idea if you have a strong acid like HCl, for example, with a weak base like ammonia. So if you've added just a tiny bit of H pluses, then you have some leftover ammonia, you are going to also form some ammonium ion. And so ammonia with ammonium ion, that is a buffer, right? Weak base and its conjugate, or in this case, weak acid and its conjugate is buffer. And so that would be a very slow change in pH, again, because you have a buffer. So that's kind of College Board's goal of teaching you about buffers, is for you to appreciate or understand what is happening in a titration. So there are 4 different types of titrations that we're going to study here. We have, depending on the strength of the acid and the base. So we have strong acid, strong base. So something like HCl and NaOH reacting together, for example. And so this is the molecular equation. So HCl plus NaOH yields water and NaCl. If you were to write the net ionic equation, since Cl minus and Na pluses are just spectator ions, you see them here, cancel them out. So you can write it as H plus OH minus yields H2O. So whenever you see a strong acid, you can write it as H plus. Whenever you see a strong base, you can write it as just OH minus. Now, if you look at this, whether you look at this reaction, the net ionic or the molecular, you'll see that at the end of the reaction, when you've reached your equivalence point, when enough HCl has reacted with NaOH and you don't have any left over HCl or NaOH, what you're going to be left with is just the products, which are H2O and NaCl. H2O is neutral, NaCl is also neutral, and so your pH is going to be 7. The pH is equal to 7 at the equivalence point only for strong acids and strong bases. So when you react a strong, that's when your pH is 7. If it's any other scenario, the pH is not equal to 7. So only with strong. The reason is your salt here is a neutral salt. It does not undergo hydrolysis. Its pH is 7, and so you end up with a pH 7. Now let's look at a weak acid with a strong base. So weak acid, an example of that is HCN or HF or acetic acid or any weak acid, and we're going to react it with a strong base. So for example, NaOH. Well, when those react together, this is a molecular equation, right? So you form water and then NaCN, right? If you were to write the net ionic equation, the Na pluses are spectators, and so you can cross those out. HCN is a weak acid, and so that's molecular, so you can't write it as H plus because not all of it ionizes, right? Most of it remains as molecular HCN, just a tiny bit ionizes into H plus and CN minus, so you can't split it up. And so you write HCN. This is a strong base, so you can write it as OH minus because that completely dissociates. You get H2O and CN minus. The pH here, when you've reached the equivalence point, when you don't have any more NaOH or HCN, is not equal to 7. And here's the reason. The reason is because the CN minus can undergo hydrolysis. And so when you have CN minus with water, it undergoes hydrolysis and you form HCN and OH minus. This is an equilibrium. And so since we're forming hydroxides, the pH is actually greater than 7. So when you have a strong base with a weak acid, the pH at the equivalence point is greater than 7. It's not because you say, oh, well, the base is stronger than the acid is weak, and so strong base, so you're going to have a pH greater than 7. That's not the reason. The reason is because one of your products undergoes hydrolysis to give off OH minuses, and so your pH is greater than 7. Let's look at a strong acid, weak base this time. So strong acid like HCl, for example. Weak base, an example of that is ammonia. This is your molecular equation. your net ionic equation? Well, because this is HCl, it's strong, it 100% ionizes, so I can write it as H plus and Cl minus. And so the Cl minus is a spectator ion here and here, so it cancels out. So I can just write it as H plus. This is a weak base, so I have to write it as is, as NH3. And then we've said that the Cl minus cancels here because it's a spectator, so you end up with ammonium ion. When that happens, your product, the NH4 plus, the ammonium ion, can undergo hydrolysis. And when it undergoes hydrolysis, you form an equilibrium. You get NH3 and H3O plus. So since you're getting hydronium ions or H pluses, your pH at the equivalence point, when you've used up your acid and your base, is going to be less than 7. Again, it's not about strong acid, weak base, so the strong acid wins, and so my pH is lower than 7. No, the reason is because your product is an ion that undergoes hydrolysis and gives off H pluses. If you have a weak acid and a weak base reacting together, so like HCN and NH3, for example, this is your molecular equation. Basically, both of your ions here can undergo hydrolysis. And so there is no way for you to know what the pH would be at the equivalence point because the NH4 plus undergoes hydrolysis to form H pluses. The CN minus undergoes hydrolysis to form OH minuses. And so it depends on which one has a higher Ka or Kb. Is the Ka for NH4 plus, or is the Kb for CN minus larger in value? And so the one that is larger is going to basically produce more of those ions, and the pH will be either higher or lower than 7, depending on which one. So we are going to do calculations with strong, strong, weak, strong, and strong, weak. We are not going to do calculations with weak, weak, but you do need to know that the pH at the equivalence point is not necessarily equal to 7. Because of the hydrolysis of the ions, you need to be able to write the equations for the hydrolysis of the ions. Now let's look at our curves here. These are titration curves for the different types of titrations. And you'll see that when you have a strong species, the lines are longer and sharper. So for example, here, this is strong, strong. See how the lines are longer and sharper? Here we have a strong base, so this line is sharper. This is a weak acid, so this line is kind of curvier. Here we have a strong acid, weak base, so you'll see that the one that's weak is shorter and curvier. The one that's strong is longer in a sharper corner here. And then this one's weak, weak, so very short and very curvy as well. So that's something to keep in mind. The stronger species will make your titration curve longer and sharper. The weaker species will make it shorter and curvier. Also note the equivalence point. So this is strong, strong. So the pH at the equivalence point is 7. To find your equivalence point, what you do is you see where the inflection points are. So right here and right there, and halfway between the inflection points is your equivalence point. So right here, that's a pH of 7. This one's a weak acid with a strong base. And so your inflection points are here and here. So inflection point is where the curve turns, right? And so halfway to the inflection point is right there. And you can see that that's a pH a little bit higher than 7 because it's a weak acid, strong base. So your anion at the end can undergo hydrolysis to give off hydroxides, and so your pH is larger than 7. This is the strong acid, weak base. So if you look at your inflection points and look halfway there, that is a pH that is a little bit lower than 7. That's because your product is a cation, that can undergo hydrolysis and give off H pluses, and so it's acidic at the equivalence point. With weak acid, weak base, you can't really tell. Depends on what the species are. But if you look at the inflection points and read the pH, again, it depends on what it is. Sometimes it's 7, sometimes it's below 7, sometimes it's higher than 7. So with strong, strong, see how this line is really, really long? It's a little bit shorter when it's weak, stronger, strong, weak. and it's really short when it's weak. Back to the difference between the equivalence point and the endpoint. So the equivalence point is halfway between the inflections. That is when enough acid and base have reacted completely. So you don't have any leftover acid or base from your reactants. The endpoint is where the indicator changes color. So you want to pick an indicator that will change color at the equivalence point given. So for example, if you have a weak acid, strong base, because your pH will be higher than 7 at the equivalence point, you want to pick an indicator that maybe turns at pH of 8 or 9, just a little bit above 7. If you have strong acid, weak base, the pH at the equivalence point will be lower than 7, so you want to pick an indicator that will change color maybe at pH of 4 or 5 or 6, something like that, a little bit lower than 7. But the longer this vertical line is, the more leeway you have. So something that's strong, look at this. Basically, the same volume of base, like 1 drop of base, will change the pH from like 2 to like, I don't know what that is, 9 or something like that. So it's very, very vertical. And so that means any indicator that will change colors in any of that vertical region will be okay to use. Whereas when you get to something like this, you want to be more careful with your indicator because you need an indicator that will change just in this region. You only have like 1 or 2 pH units where you can have that vertical region where you don't have a difference in the volume of the base. So the longer that vertical line is, the more leeway you have with an indicator. So a strong, you can use almost any indicator really that will turn colors from anywhere from here up to there. So this is an overview of titrations. Like I said, in the next couple of lessons, we're going to study how to do calculations in titrations of different strengths of acids and bases.